Hi, so this is the second lecture in the series of lectures about ancient solutions to geometric flows. And as you recall, in the last lecture, we defined ancient ovals, which will play an important role now. And I will remind you that ancient ovals are closed, alpha non-collapsed, and convex ancient solutions to the mean curvature flow, which are not self-similar, because if they are self-similar, then we know that they have to be round spheres. Okay, so the question is, how do we know that they exist? So here is, I'm going to tell you about the existence of ancient ovals. And this is the result due to Brown-White and Hasselhofer, Hershkovich, independently, who gave more details about the construction. And as you will see, the solution is not given by the explicit formula, but it is just a constructive way of proving of its existence, right? Okay, so what they show is the following: for every j in between 1 and n minus 1, there exists an ancient solution, m sub t, subset of Rn plus 1 with O j plus 1 cross O n minus j symmetry, so that, right, of the mean curvature flow, so that it has convex time slices as t approaches to 0, it converges to a round point, because it is convex, and we have the result of Huskin, and we have the following asymptotics as t approaches to negative infinity. As t approaches to negative infinity, we can see something which is called the asymptotic shrinker. Okay. So what does that mean? This means that for lambda going to plus infinity, parabolically rescaled, flow, which I'm going to call lambda inverse m lambda squared t, converges, of course, subsequentially to a round shrinking cylinder. Okay, which is actually a generalized cylinder as j, where it is of the radius square root of 2j times negative t, and then cross Rn minus j. So this is a generalized cylinder, right? So this means that we see somehow this asymptotic shrinker, which is buried into our ancient solution, right? So if we parabolically rescale, right? So this means that we just, like, as time approaches to negative infinity, our ancient solution looks more and more like this generalized cylinder. And then the second thing is what we see is the asymptotic translator. Okay, so how do we see that? Well, rescale around the tips. P sub t by the mean curvature at the tips. Then, as tk approaches to negative infinity, we get convergence to a translator. Okay, which is the ball soliton that we discussed in the previous lecture of dimension j plus 1 and cross Rn minus j minus 1, right? So since our thing, right, is rotationally symmetric, so it looks like this, and we will refer to the tips as to these points, which are also the points of the maximum mean curvature. Okay, and what we will focus on the case when j is equal to n minus 1. So in which case that after parabolic rescaling, so here you will just see, right, a round cylinder Sn minus 1 cross r, right, and around the tips, if you perform rescaling, you will just see n-dimensional ball soliton, right, in this case. And that will be our focus. Okay, so I will also remind you that this ball soliton that we mentioned in the previous lecture, right? So Bn opens up like a paraboloid. It's rotationally symmetric. It's a unique rotationally symmetric convex solution. To the translating equation, has like the maximum mean curvature at the tip, and it's graphical, right? And its height function satisfies the equation uxx over 1 plus ux squared and plus n minus 1 ux over x is equal to 1, right? So this is the equation of the ball soliton. And now I'm just going to tell you in a few sentences how this ancient oval has been constructed, right? So we take a truncated cylinder Sn minus 1 cross minus LL. And of course, you can carry out this similar construction for every J. So here we take a truncated cylinder of size 2L, right? And then you cap it off on both ends with caps of a unit size, right? So the size of these caps is independent of L. Okay, and this will be my hypersurface, which I'm going to call L, and that will be my surface at time t is equal to 0, and then we will evolve it by the mean curvature flow to produce, right, the flow, which I'm going to call ML, or maybe MLT, okay, TL. So maybe we will put this L just in the subscript, right? Okay, so we will produce this flow, and then we know that it exists from some 0 to some singular time t sub L. And by using cylinders as the interior from outside and spheres as the barriers from outside, and using the spheres as barriers from inside, you can actually show that this TL is comparable to 1 as L approaches to infinity. Okay, and now what you do, you rescale this, right? Rescale this flow to get a rescaled flow, which I'm going to call M sub hat LT, right? Where T now belongs to TL hat up to 0, right? Where TL is strictly less than -1, so that, right, the first thing, the flow becomes extinct at time t is equal to 0, right? And then the second, right, we can look at the major radius A of t, which I will define to be the maximum as x lies in M hat LT of the the absolute value of xn plus 1, and that will be the major radius. And then the minor radius b of t, which is just the maximum over x in M hat LT of the sum when I goes from 1 to n xi squared, and then you take the square root of that. And then what you look at is this ratio A of t over b of t, right? So, and you will rescale your original mean curvature flow to produce this rescaled flow, first of all, so that the extinction time is 0 for every L, and the second, so that this the ratio of this radius is equal to 2 for the first time at time t is equal -1, right? So because you start with something which is very elongated, right? So you can make initially this ratio arbitrarily big, but as t approaches to 0, you know that your flow converges to a sphere, but this ratio is converging to 1. So that means that in between you will have some time at which this ratio is equal to 2, right? And you will rescale your flow so that the first time at which it becomes negative, at which it becomes 2 is equal to -1. And then you will argue, then you have to prove that the limit of t hat L is equal to negative infinity as L approaches to infinity. And you have to argue, of course, that you can take the limit of this sequence as L approaches to infinity to produce the ancient solution, which I'm going to call M infinity T. Okay, and T, right? And now T goes all the way from negative infinity up to 0, right? And this will be our ancient solution, right? Which will have the property that at time T is equal to -1, this ratio of the major and the minor radius is equal to 2, which means that our limit cannot be like the ancient solution that we already know from before, which is a sphere, right? It has to be something else. That's how they, right, they prove the existence of this ancient solution, which is not a sphere and which is not self-similar, because if it were self-similar, we would know it has to be a sphere. Okay, so now let's define MT to be uniformly convex if there exists alpha greater than 0, so that lambda 1 plus lambda 2 is greater or equal than alpha times h, right? Where alpha, lambda 1 and lambda 2 are the first two smallest eigenvalues. And what is known that this condition is preserved along the flow, right? So what are the candidates for ancient, non-collapsed, uniformly two convex, convex ancient solutions? Okay, so let's just write all possible candidates, and these are the spheres, right? And then round cylinders, the n-dimensional ball soliton, and the ancient oval. Okay. Okay. So these are all candidates that we have listed and we mentioned before. Now what our goal is to show that these have to be the only ones and there is nothing else besides them, right? So there is a theorem of Brandle and Choi to prove the following. So if MT, T is in negative infinity to 0, is non-compact, convex, uniformly two convex, and non-collapsed, ancient solution. Ancient mean curvature flow solution in Rn plus 1. Then it is unique, rotationally symmetric, translating solution, which is the ball that we have already mentioned several times, or a round cylinder. Sn minus 1 cross R, right? So this means that basically, so here, if you have this condition on being uniformly two convex, right, then you are getting this cylinder, round cylinder, Sn minus 1 cross R, right? Because like this K convexity would correspond to other generalized cylinders. But since we are putting this assumption onto convexity, then the only one that you can see is this round cylinder Sn minus 1 cross R, right? So this is the theorem of Brandle and Choi. And then as a corollary, they prove the following: let M naught be a closed two convex hypersurface that evolves by the mean curvature flow, evolving by the mean curvature flow. The only possible blow-ups are at the first singular time Sn minus 1 cross R, or the n-dimensional ball soliton, right? So this means that if you study the evolution equation of closed two convex hypersurfaces, and recall that two convexity is preserved along the flow, and if you want to study the singularities, right, then you can take any blow-up limit, which means that you take any sequence PITI converging to a singular point, and you rescale by lambda I going to plus infinity, then the only possible limits that you can see this way are the one that I have listed, the spheres, the round cylinders, or the ball solitons. Okay, so this is like the corollary of their result. So now if you look at the list of these candidates here, right, so for these ancient solutions which are uniformly two convex, you can see that if you have a complete non-compact ones, then the only possibilities are the round cylinders and the ball solitons due to result of Brandl and Choi, right? So now what we are interested in is like what happens in the compact case. Then we want to say that there's nothing else besides the round sphere and these ancient ovals, right? And this is like what I'm going to state in the next theorem. Right, that's the theorem with Angenent and the Skolopoulos and myself, which says that the only compact, non-collapsed, uniformly two convex ancient mean curvature flow solutions are the spheres and the ancient ovals up to translations and scaling. Okay. So here, like we have theorem of Brandl and Choi, which I will call theorem 1. And then this is our theorem, which is theorem 2. And now I will say in both theorems, okay, there are two parts that you need to be proved. Okay, the first one is establish rotational symmetry. Of the solutions. And then second, like under rotationally symmetric assumption, we show the uniqueness result. Under O of n symmetry. Okay, so in both theorems, you first establish that the solution has to be rotationally symmetric, and then once you know it's rotationally symmetric, then you establish the uniqueness. It's just that, like in the complete non-compact case, since you just expect to have those translating solutions and the cylinders, which are the solitons, then the proof is a little bit different. It's enough that you prove that your solution like has to be a translator if it's not a round cylinder, and then hence by the uniqueness of rotationally symmetric ones, rotationally symmetric translators, you have to have the ball soliton, right? But like in the compact case, like since ancient ovals do not satisfy any, they are not self-similar solutions, they are not translators, then the proof has to be completely different to prove the uniqueness, right? So now for simplicity, I'm gonna now assume that my flow MT, T less than capital T, is ancient oval with ON cross O1 symmetry. This means that just it's rotationally and reflection symmetric. But we of course prove that every such solution has to be reflection symmetric. So that's not really a hypothesis, but just for simplicity, I'm going to assume this here. So which means that my ancient oval I can write as X, comma X prime in R cross Rn, okay, where X is in between negative D of T and D of T, right? And the norm of x prime is u of x comma t, where u is my profile function, right? And then mean curvature flow equation is equivalent to the evolving this u by the following equation. Okay, let me just use some color. So I'm going to write the dt of u is uxx over 1 plus ux squared minus n minus 1 over u, right? So this is like the equation that you will study in this case. And then since you want to see a cylinder right in between, you need to perform the parabolic scaling. So let me tell you how you perform the parabolic scaling of your solution, right? Parabolic scaling. So m sub tau is t minus t to negative 1/2 mt, and tau has to be negative log of t minus t. So why is that? Give me just 1 second as I close the window because there is a lot of noise coming from outside, right? So this is the parabolic scaling that we perform, and we need to do that because, like, if you remember our ancient ovals, as time approaches to negative infinity, if we don't rescale, they just become longer and longer and thicker. So if we don't rescale in the limit, we will not see anything. So you have to like rescale, so like to make this width bounded, so that when you take the limit, you actually get a round cylinder in our case. And I'm gonna just write the equation in this case, right? So my little u of y comma tau, which is the rescaled profile function, is big U of x comma t divided by the square root of t minus t, and y is x over square root of t minus t, right? So this is like how the profile function scales, and then the equation that it satisfies is du d tau is equal to uyy over 1 plus uy squared minus y over 2 uy minus n minus 1 over u plus u over 2. Okay, and then I'm going to also say that the limit of u of y comma tau, we know that as tau approaches to negative infinity, is square root of 2 times n minus 1, because u is equal to square root of 2n minus 1 corresponds to a round cylinder, right, whose cross section is of the radius square root of 2n minus 1. Okay. And then I will just briefly say that we measure the deviation from a cylinder. So we introduce a function u, so function v. So u is square root of 2 n minus 1, and then times 1 plus v. Okay, and v is the deviation from a cylinder, right? So now, like, how does our solution look like? So here is my solution, right? So here it looks like cylinder. So this is cylindrical. Right? And here around the tips, it has a different behavior, looks like the ball solvitum. So like in proving the uniqueness, we want to consider the difference of the two solutions and prove some weighted L2 estimates in these two different regions, the cylindrical region and then this ball region. But of course, we will here also put some overlap, right? And then we want to use the kata functions, right? So you want to use the kata functions, but then you have to take care of the errors produced by these kata functions. And that's why you have to measure this V, which is a deviation from a cylinder on a large region in terms of a deviation from a cylinder on a smaller region, right? So because if I know that my deviation from a cylinder on a large region, I can control by a deviation from a cylinder on this smaller region, then I could use the kata functions, and then I have hope to control the errors in this overlap region coming from kata functions. Right? So, and this is what we do by a subtle argument using the barriers. Right? So this is what we call the localization argument. Right? So once again, this is a controlling the deviation from a cylinder on a very big region by a deviation from a cylinder on a much smaller region, right? So, and then this V, you can compute that this V satisfies a very nice evolution equation. So it is V sub tau is Vyy minus y over 2 Vy plus V, and plus the error, which you can compute explicitly. And this is a quadratic term, that depends quadratically on v, the first derivative of v and the second derivative of v. And this is a very nice linear operator, L of v, which you obtain, right? If you linearize, basically what we are doing here, we are linearizing our mean curvature flow equation around the cylinder u is equal to square root of 2 times n minus 1. Right? So you get this nice linear operator, and this operator is self-adjoint with respect to the weight e to the minus y squared over 4, and has a very nice discrete spectrum, which is very well understood, and that's what we use in our analysis. So now I will just say that using localizing phenomenon, plus Merle-Zag type of ODE arguments, okay, so this is the first thing that we do, right? We show unique asymptotics of ancient ovals as tau approaches to negative infinity, right? So we still don't, I mean, in this first result of ours, we don't really prove the uniqueness, but we prove that under this rotational symmetry assumption, which we of course prove as a part of our theorem, that the solution has to be rotationally symmetric, then we prove that every such solution has to have unique asymptotics. So they almost look the same to each other. So we prove very precise asymptotics. Okay, and I'm not going to write all of them here, but I'm just going to write the ones that matter. And this is the parabolic region. So parabolic region. In the parabolic region, we prove the following. For every L greater than 0, we prove that our solution, our rescaled solution, looks like square root of 2 n minus 1, and then 1 minus y squared minus 2 over 4 tau plus little o of tau to negative 1, right, when y is less or equal than L. Right? So u is equal to the square root of 2n minus 1 is a round cylinder. So here we compute the second order asymptotics. And this y squared minus 2, it is just like the eigenvector corresponding to the 0 eigenvalue of this linearized operator L, right? Which you get when you after linearizing the mean curvature flow equation around the cylinder. Right? So this means that in these asymptotics, right? So you want to see how close to the cylinder you are. In these asymptotics, what prevails is the 0 mode, right? So the projection on the neutral eigenspace. Okay, so then I'm going to just say the following, like again, I'm going to draw this picture. So this is what is happening in this parabolic region. Then of course you have the tip regions here, right? And then you have something which connects the two regions, which we also call the intermediate region, right? So this is here, the intermediate region asymptotics. We also, by using the barriers, we exactly compute the intermediate region asymptotics, which I will not write right here, but I will just say that we have also the tip region. Okay, and that I will say that around the tips, which are the points of the maximum mean curvature, and the points where the profile function u is equal to 0, right? Around the tips, rescale by h max of tau, because at the tips this h max is actually attained. Then we prove full convergence as tau approaches to negative infinity to the ball soliton with velocity 1. Okay. So once we know that, we can discuss the uniqueness of our solutions, right? So once we have that they are almost the same, they have like almost the same asymptotic, they have the same asymptotics, they look almost the same. Now we can discuss the uniqueness. Okay, so here is one remark, that the mean curvature flow is invariant under translations in time and parabolic dilations. Okay, so which means the following: each solution M of t gives rise to a two-parameter family of solutions that I'm going to call M gamma beta of t, which is e to the gamma over 2 times m of e to the negative gamma times t plus beta. Okay, this is how you rescale the time, and we shift the time by beta. Okay, and what we show is the following. For every two ancient ovals, m1 of t and m2 of t, there exist some parameters gamma and beta so that m1 of t is equal to m2 gamma beta of t, right? So if you give me two ancient ovals, I cannot prove that m1 is equal to m2, right? Because the mean curvature flow is invariant under translations in time and parabolic dilations. But if you give me two ancient ovals, I can prove that there exist some parameters gamma and beta so that, right, these two are the same. Okay, so this means that like when we study the mean curvature flow equation and like when we do our estimates, we keep in mind we have these two parameters that we have to make use of, right? And that's why we can also prove our estimates. And here, like in proving the uniqueness, I'm going to tell you just the main idea. Is to establish sharp L2 estimates on a difference W of two solutions, U1 minus U2 gamma beta, right? But like from now on, I'm just gonna forget about these two parameters. We will just keep in mind that we have them floating around and that we have to make use of them. But for simplicity, I'm just gonna write W is U1 minus U2, which improve as tau approaches to negative infinity. Okay, so we want to establish sharp L2 estimates. We have basically two regions, the cylindrical region and the tip region. And then there is some overlap, right? So we establish L2 estimate in the cylindrical region with the right weight, which is e to the minus y squared over 4. And then in the tip region, you have to choose the weight much more carefully, right? Which is depending on this ball soliton, whose behavior you see around the tips. And then you have to make sure like that these two L2 weighted norms are in some way equivalent at the overlap regions. And then when you put these two estimates together, you get the uniqueness, right? So, but what is the obstruction in doing all this? It's neutral and unstable, or which are the positive modes, but there are only finitely many of them, of L, right? And that's where the parameters gamma and beta kick in, right? To somehow deal with these neutral and unstable modes, we choose our parameters gamma and beta carefully, right? So that these modes do not obstruct performing our estimates anymore, right? So, and here I'm just going to define for you. So I'm just going to define for you the cylindrical region. Right, C theta, that's y comma theta, so that U1 of y theta is greater or equal than theta over 2. And tip region, we have tau theta, which is the set of all y tau, so that U1 of y comma tau is less or equal than 2 theta. So you see that you have some overlap, right? So once again here, right, U is our profile function, right? It's the radius of these cross sections. This region is the cylindrical region where U is greater or equal than theta over 2. And then here you have u less or equal than 2 theta, that's the tip region, right? So you see that you have some overlap here, and then the same on the other side. Okay, and right, since you have two different kind of behaviors, you have to right, you have to like use the cutoff functions for the tip region and also for the cylindrical regions, right? And then what you prove, okay, so what you prove by doing all this and putting these estimates together is the following thing. So if I call W is U1 minus U2, and if phi C is the cutoff function supported in the cylindrical region, which I call C theta, okay, then let me call WC to be W times phi C, right? And then I'm not going to go into the tip region, but I'm not going to write the estimates exactly what we prove, but like I will just remind you again, you have to construct weights carefully in the tip region. In the cylindrical region, you use the estimate, you use the weight coming from this linearized operator L, and you have to make sure that in the overlap region is two L2 norms, weighted L2 norms are in some sort of sense equivalent. You prove the estimates, you put them together, and basically then what you prove is the following thing. The norm of WC at tau, right, where the weight is taken with respect to e to the negative y squared over 4, is equal to the norm of P0 WC of tau times 1 plus little o of 1, okay, as tau approaches to negative infinity. And what is now P0? P0 is the projection, okay, P0 is the projection onto neutral eigenspace of our operator L. Okay, so this means that if I take the difference of two solutions, U1 and U2, I can carefully choose my parameters gamma and beta, which correspond to translations in time and parabolic dilations, right? So that the norm of the difference, right, is dominated or like behaves like the norm of the projection onto neutral mode. So the projection onto neutral mode is what dominates. And then, so this is the estimate that once you have it, you can project your equation, the whole equation, onto neutral space. You can carefully analyze the error terms, and then you can prove that WC of t is identically equal to 0. Because what we actually prove is that this projection onto neutral mode is identically equal to 0, which gives you also then that WC has to be equal to 0. And then you also argue that W is identically equal to 0, which means U1 is equal to U2 gamma beta for some choice of parameters gamma and beta. Okay. Okay. So the theorem, the second theorem that we proved that actually puts all this together is also the theorem with Angenent, Daskalopoulos, and myself. And it says let M sub t, where t is in negative infinity t, be an ancient oval that is uniformly two convex, then it is rotationally symmetric. Okay, so this is the second theorem we have. And then once you put these two theorems together, you will obtain the complete classification of closed ancient ovals, which are uniformly two convex. As I stated at the beginning of this lecture, they have to be either the spheres or these ovals that are constructed by Brian White or Hasselhoff-Hershkovich independently. right? So we have the uniqueness of the ancient topology. So what I'm gonna do, like in the last lecture, I'm just gonna give you some ingredients of the proof of this theorem and give you some applications of the techniques that we developed in the course of proving these theorems. And then I'm going to also tell you how they apply to proving something similar in the Ricci flow. Okay, thank you for your attention.